Hi folks. Today we're going to talk about compound and simple interest and look at the difference between linear functions and exponential functions. So let's get started. So we're going to begin with a simple interest question, and suppose you invest $5,000 earning simple interest with an annual interest rate of 10%. How much money will you have after 5 years? So basically our $5,000 is earning 10% every year regardless of what year that is. So the way we can always find that answer is take 5,000 times 1/10. And we can see that in the first year, we can take 5,000 times itself, which is represented by 1, plus the 1/10. So this gives us 5,000 times 1 and 1/10, which is 5,500. We can keep on applying this process until we come up with 5 years. So the next year, for example, we take the 5,500, and then we're also applying the 10% to the 5,000. So this gives us 5,500 plus an extra 500, and we get 6,000. And if we go on to year 3, we can see something similar because we're applying that 10% interest to 5,000. We add an extra 500 to the previous line to get 6,500. Year 4 is more of the same. We add another 500 to the previous line, which is 7,000. In year 5, finally, we add our previous line with 500, and we get our final answer of $7,500. Now, this might seem like an easy task, but what happens if I ask you for, say, 10 years or 30 years or 40 years worth of time? This would be kind of a pain going year by year. So we try and cut down on this process and actually move forward with finding an answer. So let's revisit years 2 and 3 and see if we can find another way to look at those. So for year 2, when we take a look at that, if you see the 5,500, if you notice in the first line, we could write that 5,500 as 5,000 times the quantity 1 plus 1/10. And I'm going to write that right there. And then also add in year 2, you have that 5,000 times 1/10. But notice with the 1/10, you have one term appearing in the first quantity that has 5,000 and a second 1/10 term appearing in the second piece. So if you add, you have 1/10 plus 1/10, that's 2 times 1/10. So another way for us to write this is 5,000 times the quantity 1 plus 1/10 times 2. In other words, we get our 6,000 just in a different format. So year 3, I want to emphasize we can use the previous line. We know what 6,000 is. It's 5,000 times the quantity 1 plus 1/10 times 2. And then we add in that extra 10% on the 5,000. But if you notice, you have the 1/10 times 2 in the first spot, and then you have another 1/10. There's only one of them in the second. And what that leads us to is we have 3 of the 1/10s. So we could have rewritten this line as 5,000 times 1 plus 1/10 times 3. So with our 6,500 and our 6,000 for our answers for year 2 and 3, notice that we can look at the years, and that corresponds to the number multiplied by the 1/10, which is representing our 10% essentially. And this gives us a nice idea for actually finding a function for simple interest. And that function is just taking this a of t equals p times 1 plus rt. Now, let me explain what each of those are. The P is our principal investment, so that's what we're starting with in terms of income. Our R is just our annual interest rate, but we're writing it as a decimal. Our T is our time in years, and we can actually adjust. If we aren't using an annual interest rate, let's say a daily interest rate, then our time should be in days, so we can adjust accordingly. And then last but not least, the A of T, that's the investment amount, total investment amount after T years have passed. So let's revisit our problem. What is actually happening here? Well, if we're revisiting year 5, right, we are looking at our principal investment is $5,000. That's how much we started with. Our annual interest rate, that's actually 10%, but we want to write it as a decimal, so that would be 1/10 or 0.1. Our time in years is actually 5 years, and hence the year 5 revisited. And so now we just want to find that amount or for our total investment after t years have passed. Well, in this case, t is 5, so we have a of 5, and that should equal 5,000 times 1 plus 1/10 times 5. You can simplify that to 5,000 times 1.5 or 7,500. Notice this was a lot quicker than going through all those steps to get our answer. So this is kind of our goal, is to cut down on the time spent on each problem, and that's what this function comes in handy. In this example, if you notice, the t, it appears as a linear term because t is raised to the first power. I know you may think there's multiple variables, but p is a constant, the r is a constant. T is a variable here. So we have a linear function is what's being represented anytime we're dealing with simple interest. So moving forward, what we want to do is compare this to compound interest. And what compound interest does, all of the other things are the same. I'm keeping the income invested at the $5,000. You have the 10% for the annual interest rate, 5 years, so the time is the same. Only difference is this is compounded annually. So with that compounded annually, this becomes a different ballgame. What that means is not only is the original 5,000 earning interest, our interest is actually earning interest. So for example, the first year will remain exactly the same as what we saw before, the 5,500, but instead of the 10% being applied to 5,000 now, we want to apply the 10% interest rate to the $5,500. And the way that looks is take 5,500 times essentially our 1.1, and that gives us $6,050. Now we want to apply the 10% interest to the 6,050 to get our year 3 outcome. And so you take the 6,050 times 1.1 or 1 1/10, and that's 6,655. Once again, we're applying the 10% interest to the year 3 outcome. So 6,655 times our 1.1, and all of a sudden that gives us $7,320.50. Finish that with applying the interest to the $7,320.50, and we actually get $8,052.55. But as we did before, we want to find a quicker method for finding our answer. So with that in mind, when we revisit the year 2, notice we have 6,050, but another way to write 6,050 is going to be the 5,500 times 1.1, and the other way to write 5,500 times 1.1 is going to be 5,000 times 1.1. So putting all this together, you get 5,500 times 1.1. That's the same thing as 5,000 times 1.1, and then we still have that extra 1.1 out multiplied by that. But you have 1.1 times 1.1. If you multiply those two together, another way to write that is 5,000 times 1.1 squared. So 6,050 is the same as 5,000 times 1.1 squared, whereas year 3, if we take the 6,655, you can write that as 6,050 times 1.1, which is the same thing as 5,000 times 1.1 squared times another 1.1. Well, if you multiply 1.1 squared and 1.1, that gives you 5,000 times 1 1/10 cubed. Notice the years here. So year 2 revisited, that 2 appears up in the exponent on the 1.1. In the third year, the 3 appears up in the exponent on the 1.1. So basically our time should be appearing up in the exponent. And there's one extra piece that we're going to have to account for, and that's how often we're compounding these things. And this gives us our formula for compound interest. So same problem, let's try and cut down on time. So you have a formula, A of t equals p times the quantity 1 plus r divided by n, and all that's raised to the nt power. So same old song and dance as what we did before. Our p is actually our principal investment. Our r is actually our annual interest rate, and we would just want to make sure we write it as a decimal. Our t is still time in years if we're dealing with an annual interest rate. Now the n, you see the n in 2 places. What does that stand for? Well, the n, we have to deal with it. We're compounding here. How often are we compounding? And in this case, number of times compounded per year, since we're dealing with an annual interest rate. And then finally, our A of t is still the same. That's the investment amount after t years have passed. Putting all of this information together, what do we have now? Well, we can revisit year 5, and we have our principal amount is $5,000. Our annual interest rate is 10%, or 0.1 when we write it as a decimal. Our our t value is actually 5 years, so we're good there. And our n value now, it's compounded annually, So the number of times compounded per year if we're compounding annually would be once per year. So n is actually equal to 1. We're ready to plug and chug. And so we have a of 5 equals, plugging and chugging all that information, we have 5,000 times the quantity 1 plus 0.1 over 1 raised to the 1 times 5, or the fifth power is what that becomes, 5,000 times 1.1 to the fifth power, which is what we saw before, being $8,052.50. So, putting this all together, this is actually having, when we're looking at compound interest, we have an example of an exponential function versus simple interest is actually a linear function. So comparing these two, what happens? What's actually growing faster? Well, if you look at the first answer, for simple interest, we finished with $7,500. But when we started just compounding annually, meaning our interest earns interest, we finished with $8,052.50. So that's over $500 increase in terms of our income. So in terms of the growth rate, when you're looking at a function with linear growth versus a function with exponential growth, all other things being equal, it's the function with exponential growth that's going to grow faster. Keep that in mind when you're dealing with these functions. Exponential growth is going to grow faster than the linear growth in the long run.